A very good evening to all of you. So today we are going to start the problems session for the week 12 of the course Advanced Soil Mechanics, which is taught by Professor Sridhar Shekharan, and I'm the teaching assistant for this course, Mujibur Rahman. So in the last week, we have discussed the soil yielding, and then we came across the two models which are based on the critical state soil mechanics, which is the CAM clay model and modified CAM clay model. And in this session, we are going to see or learn how these models can be helpful for understanding the failure of the soil in drain conditions, different drainage conditions. So first, we will start with the prediction of soil wear from the like we'll be using the modified CAM clay model, and we'll start with the drain test, and we will try to predict the behavior of soil failure for NC and lightly consolidated soils. So this is the typical QP plot for the drain test, in which the soil is isotropically consolidated at T dash by A, and then once it is consolidated, it is unloaded to point O, and from point O we are starting a drain test. Fine. So now, like in the previous lectures, you have seen we are extensively using P and Q plot and V versus V and ln P dash plot. However, in addition to these two plots, we will be monitoring the Q stress strain and the volumetric response versus the actual strain. And these all will be helpful for predicting the failure or the whole scenario, how the soil is a failure. It is helpful in understanding the failure behavior of the soils. So we'll be discussing the NC and LOC for drain test. As I told you that we have soil which is isotropically consolidated to a stress of P dash by A, and from here we have unloaded it to point O, and at this stress, that is P dash O, we have started the drain test. Fine. So now we know that if it is a drain test, the TSP and ESP will be similar, and it will follow with a slope of 3. So what will happen from zero to sorry from O to B? This path lies within this yield curve. Fine. So this is the yield curve for the yield stress corresponding to P dash by E. So from the last lecture, we have seen that if the state of the soil lies within this yield stress, it means that it will behave as a elastic response. It will have elastic response. Fine. So once the state of the soil passes this yield curve, then it will have a elastic response, because at that very point of time, the soil will start yielding. Fine. And also this yield curve will not be valid once the stress surpasses the speed at YA. Now, corresponding to this, we have a corresponding to this and this state, we have the critical state line NCL or ICL. Sorry, this is the normally consolidation line, and this is the critical state line. Fine. This P dash by A lies here. Fine. P dash by A. And from here to here, we are unloading it. So this is the unloading curve, and O lies somewhere here. Fine. Here. Fine. Now, from when we are loading it, when we are loading from O to B, it will follow the reloading line with a slope which is similar to the loading unloading line. Fine. Or we can say it has the same slope of kappa. And it's an elastic response, so it will follow from here 0 to from O to B. Now after B, what will happen that it will go into the plastic response. So this soil will start now yielding till it reaches to the critical state with a slope of 3. So from here to here, it will start now yielding, and it will reach the failure. So from B to F, it's a kind of a plastic response, and here the soil will start yielding and reach the critical state. So if we like in the previous plot set, we are discussing the Q and P and V and ln of P dash. We will first discuss these two. After that, we will come to here. Or simultaneously, we can use these. So from O to B, from the V ln of P dash, this is the curve which corresponds to O to B, which is actually the reloading. And but reloading, which in which the stress stage is less than or the stress corresponding to this stage is less than the yield stress. Now, if we talk about the Q stress strain response, O corresponds to a state where there is no derivative stress and we are loading from here. And from O to B, since it is an elastic response, so it will be a straight line from O to B, and correspondingly from volumetric strain to volumetric strain versus axial strain, this corresponds to a a compression. Fine. Now, what happens after B? Since what will happen after B, there will be a yielding of the soil to reach the critical state. Fine. So when we are saying that it will reach the critical state by yielding, we know that this B point will reach the critical state at F. Fine. So this there will be a plastic response correspond to this, which will result in the hardening of the soil. So soil will start to harden till it reaches the critical state. Fine. BF corresponds to the like the BF is the line which corresponds to the post yield stress, post yield response for of the soil once we have started loading the soil after P dash YA. And this BF response represents the hardening response of the soil, which corresponds to the state of the stress which the soil is experiencing after P dash YA. Now, after this, BF, this is the hardening response, and correspondingly, you can see since it is a NC and LOC, there will be a continuous hardening of the soil. Hardening means it will go into the continuous compression state. So there will be the volumetric strain which will be continuing. Fine. So from this response, what we can understand? What we understand is that this information was missing in previous cases. Fine. So to understand these, like to understand these things, like the response of the soil or the soil failure, these plots are very helpful. Now, one another information is missing. That's like what will happen if we take any intermediate state, where that state will lie. If we take any intermediate state, for example, this is the we are showing only 2 points here. One is for the point B, which lies on the yield curve, which corresponds to P dash YA, and we are interested at this point here. Now, what if we take any intermediate yield curve? How the response will look like, and how it will enhance our understanding on the prediction of the soil failures. Now, stress strain response curve is curved beyond B. It's true because it will be a hardening response. It's hardening plus it will be a plastic response. Yield surface curve expands and previous yield curve is no longer valid. This is true. Like once our stress state exceeds the speed dash by A, then this yield curve becomes invalid, and whatever be the stress state after that will be there. The corresponding stress curve or yield stress curve will be valid. Now we will take some intermediate yield curve which corresponds to P dash YC. P dash YC is actually some intermediate curve like intermediate yield stress. Fine, at which the soil is yielding. It has not reached the failure yet. It's yielding. Now QR is the unloading line correspond to P dash G. Now see, here is the trap. P dash by A was the earlier yield curve. Once the soil state is experienced into a stress greater than this P dash by A, what will happen? There was a compression, correct? This part was there, compression, and this is a plastic compression or plastic strain. So what will happen? It will cause a compression in the soil. So that's where our state will change from this to this. Fine, from here to here. So this amount of compression that has occurred in the soil, it's due to the increase in the stress from P dash YA to P dash YC. Now from Q, if we unload the sample, this whole whatever the stress state will be less than P dash Y, they will have a elastic response. So this was the unloading line. Now the point C, this point, it will not lie on this point, this unloading curve. Why? Because some amount of plastic strain has been accumulated in the sense. That's why it has moved to this point, and this C will lie on the point C. C is some intermediate point. This will lie here. Correct? Fine. Fine. Now after that, once we exceed this P dash or we surpass the stress state of the soil, after this P dash Y dash, P dash Y C, there is the we can say it is the failure. So if we consider some more like this yield curve, so we will get similar kind of behaviors. So shearing can be done from P dash YA. Sorry, unloading from C will follow QR. That is true because it is an unloading line which corresponds to yield stress of Q. On further shearing, it fails at F. So the main thing So introduce this intermediate yield curve was to let you understand that it is not a simply a line. There is some intermediate states between the speed dash by 8 to the state of the soil at which it is the critical state which needs to understand. Fine. Now shearing also can also be done after p dash. Why? Like this is a point which corresponds to NCL. This it's actually at the yield stress point. So we can start the sharing from here also. Elastoplastic sharing occurs from P-dash to failure. Since this point lies on the verge of this plastic and elastic response. So once we start sharing from here, abruptly there will be elastoplastic sharing, or we can say there will be the strains which are irrecoverable. Fine. Now prediction of NC and LOC for the CU test. Now we want to predict the failure for the NC and LOC for the CU test using the modified Chemical model. Now we will take the advantage of all the four plots in this discussion. So we have Q P dash, we have V ln of P dash, we have Q axial strain, and in the CU test we are more interested on the excess pore water pressure, or what is the grade, what is the rise in the pore water pressure. Fine. So we'll start like since again this P dash y is the initial like the soil has been consolidated to this point P dash y A. After that there is unloading so as to create this LOC state. Now we know that if it is a if it is a undrained test and the soil is behaving as a elastic, the response is elastic. What will happen that ESP will be a perpendicular line to the P dash, or it will be a straight line till it touches the B dash. Now for this part, how this will look like? So this is the NCL, this P dash y lie here. This is the unloading curve, correct? This O and B dash will be on the same point. Fine. This it is P dash O. Fine. Now from here to here, O to B, this is the elastic response because this stress states lie within this yield surface. So the response will be it will be a elastic response. And for this amount of compression or this amount of stress, there will be a rise in the pore water pressure because this is a NC and LOC. There will be generation of positive pore water pressure, and because they lie on the left side of DSP. Now, once it crosses this B state, what will happen that there will be the it will reach the critical state by softening. It will reach the critical state. It's not like softening, sorry. So it will reach the critical state by hardening. So it will reach the critical state. Now this part, how it lies. So from B to C, we can see how the stress strain response lies. Fine. It is a straight from O to B. After that, it's a um, non-linear response. And similarly, from here, if we draw this point, which is OB, how it looks like on the critical state, it will be a straight line because we know that it's undrained test. What will be the initial specific volume? It will be same as the final specific volume. So this will correspond to a straight line. Fine. And C is some intermediate state. Now corresponding to this part of the curve BC, we have this stress strain response, and corresponding to this BF, the rise in pore water pressure is BCF. Correct. So again, after yielding, you increase non-linear. There is no linear increase in the pore water; it's a non-linear response. So from here also we can understand that how these all four plots are helpful for understanding the behavior of the soil corresponding to the undrained test. Fine. Now similar to this, we have the prediction of for the heavily overly consolidated for CD and CU test. So P dash y, corresponding now for generating this HOC, our unloading point should be very far from the P dash y. That's what we have done here. So this is a kind of a from here soil has been consolidated up to this point P dash y to a stress corresponding to P dash y. Then we have unloaded it to P dash O. Now corresponding to this is the unloading line. Fine. Now if we are loading it from O to B, it will achieve the peak state because it is a heavily overly consolidated soil and it has to reach the first yield surface that it will start to yield. So it will follow the 3:1 plot like TSP and ESP will be same, right? So what will happen that O to B it will be elastic response, that it will be a straight line from here to here. You can see from O to B it's a compression and volumetric strain will be there. Once it reaches the peak state or the yield surface, after that it will start to yielding and it will follow the same line because it's within this elastic state. Still, it's in the elastic state, so it will fall on the same line and reach the critical state BF. So this is the response which corresponds to BF. And this BF in the stress strain plot represents the softening. And softening means there will be the like the decrease in the pore water pressure, which will sorry, there will be the kind of expansion in the soil, which corresponds to BF. And here you can see there will be initial compression followed by the gain in the specific volume. You can see there is a gain in the specific volume, which will cause the expansion of the soil. Now, for the CU test, how it will look like? We know that for the CU, there will be the generation of negative pore water pressure, which will cause the section and which will like move our stress path to the right. Now, this is the stress path. This is the initial consolidated state. P naught is a reloaded. This is the unloading point. From here to here, we are unloaded to point O. Correct. So this is corresponding P dash by A. This is the unloading line, and from this O point, our stress path will move straight because it's if we talk about the elastic response till it reaches the yield surface line. Fine. So O B dash will be the same point here. Once it reaches the yield surface line, it will start to yield to reach the critical surface. Now from here to here, it will be a kind of a like a yield. It will start yielding and reach the critical state at F. Now from O to B, it will be again elastic response that we can observe from the straight line O to B. From B to F, it's a yielding or a softening. From B to F will be a softening, and correspondingly, you can see from here it will move from B to F, which will be at a like there will be a decrease in the mean effective stress, or decrease in the stresses, which will cause the failure, and this occurs at a constant specific volume. Now, from here to here, there will be a compression, fine, followed by the pore water pressure will increase first from here to here. After that, there will be a decrease in the pore water pressure. This can you can see this. If we draw the TSU, which will be at a slope of 1:3 or 3:1. Sorry. So this state lies to the left of the TSU. It will be a positive pore water pressure, and this final state is on the right of the TSU, which corresponds to the negative pore water pressure. So we can see that how the failure can be explained in a proper way or in the framework of critical state soil mechanics using these Campbell and modified Campbell models. Now, effect of the effective stress pass on failure. Now, for example, if we have this ESP, effective stress path, and we know that slope of CSL is given by M, and if the ESP or the slope of this ESP, effective stress path, is less than M, we can see the soil will not reach the failure. It will not touch the critical straight line. So, slope of ESP will influence the manner in which the failure occurs. ESP1 will not produce failure because it's not going to touch the critical state line. Fine. Now, if we talk about ESP2, which has a slope like again, it's greater than the CSL. Fine. So ESP2 corresponds to NC or LOC soil. Fine, because this is kind of unloading applicable for excavation. This is the unloading case. Yielding has to take first before failure. So what will happen that it will first go here after touching the yield surface, it will start to yield and reach the critical line. So initial point is NC or LOC. However, sharing behavior is similar to HOC. So sometimes we will get this behavior even for the NC or LOC soils depending upon the ESP, like how we are actually maintaining how we are loading the sample. Fine. How we are actually applying the sigma 1 and sigma 3 on the sample. After that, we have this determination of soil stiffness. Soil stiffness is actually characterized by the elastic modulus E dash G and bulk modulus. So these are the equations that have been formulated in this like using the critical state parameters. So you can check like these are the formulations, right? And now variation of soil stiffness with the strain levels. Now how the strains these K, G, E dash are getting affected by the strain levels. So you can see the curve. It has three regions: small strain region, intermediate strain, and large strain. Also within this small strain region, there is less degradation of the soil stiffness, which means that up to this percent of strain, we can consider the soil is in the elastic state or elastic response is there. But once the soil shifts to this intermediate zone, which is from 0.001 to 1%, you can see there is a drastic reduction in the soil stiffness. Fine. So at intermediate state, stiffness reduces and soil behaves like an elastic velocity. However, once it surpasses 1% of strain, so stiffness again becomes constant as the soil approaches the critical state. Fine. So this is the variation of the soil stiffness with the strain levels. Now, till now we have deal with the stresses like yield stresses and all. Now we want to determine the strain, that is the volumetric strain corresponding to the plastic and plastic components. Fine. So what is the procedure for that? We will see. So as you see that as this was like, for example, if we talk about the state of the soil, this is the soil which has been consolidated at P dash Y, then unloaded to P dash. Fine. So this is the state corresponding to P dash Y on the NCL. Fine. And this is the reloading line, correct? And this is the initial point. And A is the point which corresponds to the intersection of the yield surface with the like the stress state. Like this is the ESP. So A is the intersection of ESP with the yield surface line, which corresponds to state where the y dash is EA. And similarly, once we surpass this uh, stress state P dash Y, there will be another yield surface which correspond to the stress correspond to C here. And it will have a yield, it will have unloading line. Fine. And this B will lie on this, correct? And this B has a y dash of EB. Fine. So E and EB represents the y dashes corresponding to A and B when we have changed the stresses from P dash Y to P dash YA to P dash YB. Now total change in volumetric strain is given by the elastic component and plastic component. Fine. So if we tell the like how much is the volumetric strain, so it includes both the elastic part and the plastic part. So small increments in stress AB cause expansion of the yield curve. Yeah, small increment in stresses. Like if we have increased the stress from A to B, there's a expansion of the yield curve. It has expanded. You can see initially it was here, now it is here. Now delta E, change in the y ratio is given by y ratio at A minus y ratio at B. Now we have the equations. Either we can write in terms of the specific volume or in terms of E. Fine. Now the y ratio correspond to E for the like if we talk about the loading line, it's going to be E kappa minus E K minus kappa times ln of P dash A, and uh, ED correspond to this point. It's E kappa minus K times ln of Py dash. Fine, and here it is Pa dash. Similarly, if we combine these two equations and put the value of E kappa can be this, since E kappa is a constant term in both. We can use the equation of E kappa from this and substitute in this. So you will get Ed plus K times ln of Py dash minus kappa times ln of Pa dash. So we will get an equation Ea y dash at A is given by the y dash at D plus kappa times ln of ln of P y dash divided by P a dash. Similarly, the y dash at B are given by EC plus ln of K ln of P dash YC divided by P dash B. Now we need to find this EC and ED. So first, what we did, we formulated we related this EA with the y dash at this and this point. Now we know the relation between these two. We will use the equation corresponding to the NCL. So EC is called to N naught minus lambda times ln of P dash y dash. Similarly, ND is called N naught minus lambda times P ln of P dash Y. Sign, correct? So this corresponds to P dash YC, this corresponds to P dash Y. So again, we will use this N naught equation. Since N naught is in both equations, we will use this value of N naught from this equation in this equation, and we will get EC is equal to ED minus lambda times ln of P dash YC divided by P dash Y. Now from this equation, delta E is equal to EA minus EB, we will use the equation of EA and EB, and this will look like this. Then from equation A, we will use the relation between the EAC and ED. We will get the volumetric, we will get the delta E, the change in y dash, which is lambda minus kappa ln of P dash YC divided by P dash Y plus kappa times ln of P dash B by P dash A. Now volumetric strain, total volumetric strain can be given by delta E divided by 1 plus E naught, change in the y dash divided by 1 plus change in volume by initial volume, or change in volume divided by total volume. So total volume, if you know that phase diagram, this is going to be 1 plus E naught. So delta E you can use from here. You will get the equation for the total volumetric strain given by 1 divided by 1 plus E naught lambda minus kappa ln of P dash YC divided by P dash Y plus kappa times ln of P dash B divided by P dash A. Now, since I told you that it has both elastic components and plastic components, Now, elastic component will correspond to the I will zoom this part so that you will be able to understand the elastic component. Like the elastic component will correspond to this part, like from this part. So I will zoom it so that you'll be able to understand. Or if we are since this CB line, if there's a rebound, so this amount will be the elastic part. Fine. So A B dash A is here, correct, and B is here, B is here, and this line, this E lies here somewhere. So E is here. So this amount of like the unloading starts from here, fine, stops here. It's unloading and then reloading. If this point, if we have unloaded the sample up to E, and then again we have loaded, so this will be the elastic part. Fine. So how to determine that? So we have zoomed that. So this Fe is the elastic component of the total strain. So this is the total volumetric strain, fine. And this part is the plastic part, and this is the elastic part. That's what I told you here. If you extend this, so it will have two things: this and this. This part is the elastic part. Like this is the elastic part. Fine. So how to determine that? So Fe is the elastic component of the volumetric strain. The soil unloaded from B will move along the unloading line with respect to the maximum yield stress P dash by C. So again, like if we are unloading the soil, it will follow the same line because it is in the stiff state, stiff response. Stiff response is always elastic. So elastic strain delta epsilon P dash E is going to be delta E divided by 1 plus E naught. This E, the y ratio corresponding to E minus y ratio corresponding to B because it's same E and F divided by 1 plus E naught. So once we will use same for like same way we have done here, same thing we have to do here. We will get the relation delta epsilon P dash E is equal to kappa divided by 1 plus E naught ln of P dash B divided by P dash A, because P dash A, how it comes, because P dash E is similar to P dash A, the stress stage is same, that's P dash A. So once we get the elastic component, plastic component will be equivalent to total volumetric state minus the elastic component. So we will get delta EP, which is the like the plastic component of the total volumetric strain given by lambda minus kappa divided by 1 plus E naught ln of P dash YC divided by P dash Y. And for undrained case, we know that the total volumetric strain remains change in the volumetric strain is zero, but total volume change is zero. So in that case, plastic strain and elastic strain will be same. Now for calculating the shear strain, see we have calculated this part. Now we need to calculate this part. So we know that like this modified Campbell model follows the associated rule, which means that the yield surface curve for the yield surface corresponds to the plastic strain increment curve also. I mean the plastic potential function. So the plastic potential function will be same as the yield curve. So if we one thing, like if we differentiate that, if we get the normal on that curve, if we get the normal on this curve, we will get the we will get this plastic strain. I would say, like if we get the normal to the yield curve, but we will get the ratio of the stresses, and I'm going to say dp dash divided dq dash, and we know that there is a normality rule. So plastic strain increment for a given stress increment is normal to the plastic potential function. So delta ep that we have determined, this is perpendicular to the given stress increment in normal to plastic strain function. Like plastic strain increment, what would be increment in the plastic strain? Delta epsilon p plastic strain increment, it is perpendicular to the stress state corresponding to the it will be always normal to the plastic state function. So if we have the plastic state function, we will write tangent here. Fine. So with that tangent, we will get to know the equation or the formation for the normals. So when we get the equation for the normals, that corresponds to delta EP. Fine. So from delta EP, we will get to know the shear strain. Fine. So the first normal to the yield curve, we have the equation for the yield curve as per the modified Gamble model, which will be since it is following the associated flow rule. So equation for the potential yield function is same as the yield curve. So we'll differentiate it and equate to zero. We'll get a slope of the potential plastic potential function or yield curve. So slope is given by p dash by 2 minus p dash divided by q divided by m square. So normal to the yield curve, we know that the slope of the tangent and the normal is equal to minus 1. We will get a normal to a yield curve, that is minus dp dash divided by dq. And normal in terms of plastic strain is given by d epsilon q p divided by d epsilon p dash d. And both will have a slope of minus 1. So d epsilon qp divided by d epsilon p dash p is equal to minus dp dash divided by dq dash. Why? Because plastic strain increment for a given stress increment is normal to the plastic potential function. Fine. So we determine the normal for this equation for of a normal for the plastic potential function. And once we get the normal equation normal for this, so same increment will be there in the plastic strain increment. Fine. So that's why we equated it. Once we will equate it, use the equation that we have formulated, you will get the derivative shear. You will get the shear component. So, or we can say this slope for this line or the increment in this plastic strain increment, you will get as d epsilon q p divided by d epsilon p dash p is equal to twice neta divided by m square minus neta square. Fine. So from here you can also determine the delta epsilon QE, which is the elastic component of this plastic strain component, which is plastic strain increment vector, which is given by delta Q divided by 3G. And equations for strain are only valid for small changes in stress, and it's not possible to determine the failure strain by substituting the failure stresses. Also, strain should be calculated from the small increments of stresses from leading to failure. Like we can't if we know the stresses and the failure state, we will say okay, we will equate those. We will put the equations here. We will get the strain. It's not like that. We have to for different increments in strain, we have to determine the strain and then add them up in order to get the total plastic strain. Fine. Now, after that, we have this state boundary state. Now, this uh, what this state boundary state is like for if we have seen in the last like few weeks that we have told that this NCL is a bound is a rightmost bound, like there cannot be any state corresponding to the right of the NCL, and also there's a tension cutoff. If you are unloading the soil, we can't unload it like this. We have a cut off. Like up to this point only we can load the sample. Else there will be the tension in the soil which is not applicable. And also the soil cannot go like beyond the peak state in the if we are loading that it cannot pass the peak state if we talk about the HOCs. Now, corresponding to this, can it be a bound? Is there it is possible that there will be a boundary on the wet side of CSL? Is there any well-defined boundary on of the soil state on the wet side of CSL? It means that is there any surface which is like which is telling okay, beyond this line there is no possible state, or is there any bound on the wet side of the CSL? So this we need to determine. So we will be dealing now for understanding this. We'll be dealing with the 3D representation of critical state, in which we will integrate these two plots. So P dash is common in both. So Q, P dash, and V. If we have a critical state in a space, it's a curved. It will be a surface. And if these are the points A, B, C, and if we like extend them or like project them on the Q, P dash, we will get line this line, and if we project this A, P, C on the ground, or which is the floor, which V mu or specific volume versus P dash, we will get this line, right? So this is actually the combination of this whole is a combination of these two plots, and vice versa is also true. Now, how the drained plane looks in this 3D 3D representation. Now we have Q, we have the specific volume, and we have the P dash line. Now we have this surface CSL, correct? Now we have started with some state which corresponds to here V naught. This is the initial state. The soil has been consolidated up to this point. Fine. Since it's a like isotropic consolidation, Q will be zero, so it will start with the floor. So there will be no height in this plane, that is V P dash plane. Now, since it is a drain test, so it has to follow a 3:1 slope. So it means that it will reach the critical state. This AV will represent the critical state to reach the critical state, and the plane passing through, or the plane which on which this or the plane on which this AB will lie, it will have a slope of 3:1 with this Q P dash plane. Fine. So you can see this PQ will have a slope of 3 with respect to this Q P dash. Similarly, the slope, the plane which is passing through this AB, it should have a slope of 3. So when shearing starts, Q comes into picture. Drained ESP will lie on AP, APQBS, and the inclination is slope 3 with V dash plane. So again, it should have an inclination of 3, 3 with the VP dash plan. So line PQ in the ESP is Q dash Q P dash plan. That's what discussed in the 2D. The plane APQBS is the drain plane. So this represents the drained plane for this state. There will be series of such drained planes. So as we as we do the next test with different the stress values, we will have different drained planes. Fine. Now similar to this drained, we have the undrained. Now you can see that in this test, since we started with P with some P, fine, Q was 0. So this plane was parallel to the specific volume. Now for the undrained plane, it has a specific volume, initial specific volume. It's not going to change. So our this line will be constant. So the plane which will be the plane which will be there, it will be like perpendicular to this P V dash P versus V, and the our this stress path which will move from C to D, it will it will be on that plane V U T C. You can see how it looks like how is one is this curve is plotted, or once the soil will reach the critical state, how it is plotted, like projected to the PQ plot. And you can see the plane here is at some distance from the Q P dash. However, it's perpendicular to the I mean to say this plane P dash E plane. So for undrained sharing, ESC will originate from C and will fail on CSL in space D. Correct. So undrained ESP CD will lie on the plane C T U D V, where the initial specific volume will be same as the final, and this plane will be parallel to the this P dash Q plane, and it will be perpendicular to the this specific volume and P dash plane. So this plane is called the undrained plane, and similar to this, there can be a like the series of undrained planes possible. Like this is one, this is another, this is the series. Now we want to discuss the same point. Like, is it possible this bound that we talk about? Is there any bound for this? We will discuss that. Like, if it is possible that, for example, if there is a bound, if this is a bound, so then the specific volume should be same for a particular soil in different ESPs. What it means, like if we take the different initial states A, B, C on the wet side, so A, B, and C, they are on the wet side. It means they're on the right side of the critical state line. Fine. And AB is isotropically consolidated, which lie on the CSL. A is sheared under drain conditions with P dash constant. So it means that if P dash is constant, only Q is increasing, it will go vertically up. B is sheared under drain conditions, so B will move to the left. C is initially anisotropically consolidated at n neta is equal to Q by P. So it will have some ordinate in the Q along the Q direction. C is sheared at same isotropic. It means that we are maintaining this Q by P ratio throughout the test. So all ESPs pass through the point P. So all the ESPs, whether this one or this, they are passing through point this. So similarly, if we start at some other point, let's assume like if we see that all the three for different states, for the different states A, B, C, they are the stress paths are passing through a singular point. So to understand whether all ESPs will have a same specific volume at point P, we need to like we need to find that unique surface. Like what is that unique surface which or unique plane which will pass through these points, or in 3D how this unique plane looks like in the VQ dash P dash space. So whether different drained and drained, yes, we will have a same specific volume where across each other P1, P2, P3. We can see this is P1, this is P2, this is P3, but they are crossing at same specific volume points. So if yes, there this would result in a unique surface in VQP dash space. Now, if different ESPs have a unique point, which have a like for example, this is one like a drained ESP. This is undrained ESP. This is undrained ESP. This is undrained. Or it's a effective stress path. Effective stress path. This is a drained. So they are crossing each other at some point. So if we connect these points, is it like there will be a plane, or in the 3D there will be a unique surface which will be passing through these points? Can we call it as a bound on this surface on the wet of the CSL? We'll see that. Now that we call like state bound surface for the NC, which is on the wet side. So that's called the Roscoe surface. So experimental data, like experimentally, it has found that the point of crossing or drained and undrained ESPs have same specific volume in VQP dash space. So in VQP dash space, like they are crossing P1, P2 is the point of crossing of ESP, this ESP and TSP, this ESP, TSP, P1, P2, P3. The unique surface of state boundary surface for NC in VQP dash space is called the Roscoe surface. So the surface which is passing through this P1, P2, P3, they are called the, or this is the Roscoe surface. Like this will be the Roscoe surface for the NC soils. Roscoe surface forms one of the boundary surface beyond which soil is impossible. So this Roscoe surface is it's actually the bound on the wet side of the CSL. Correct. State bound surface for OC. Similarly for OCs, for OC we have the Hover-Slave surface. A series of undrained and drained ESPs of OC soils meet peak or yield curve and then fails. Like it will go like this and then it fails. It will go like this and fails. So this bound will be there. Like there's a one bound is a peak line, and similarly for the OCs we have the Hober surface. You can see it is well understood in the when you use the normalized plots Q by P dash and P dash B. This is the Roscoe surface. This is the yield tension cutoff, and this is the Roscoe surface. Like the SC cannot pass, HOC soil cannot pass this Roscoe surface which correspond to the peak state. So P can also be defined by this P can be either defined by power law as we saw in the previous lectures, or the Mohr columns. Peak line forms the state boundary surface for the OC. This state boundary surface for OC is called the hover slave surface. Fine. So this is the hover slave surface which is actually bound for the HOC. Fine. So hover slave surface meets Roscoe surface in the normalized plot. You can see in the normalized plot of Q by P dash and P dash by PC, they are meeting at CSL. And this hover surface is represented by this equation, and this is a 3D representation of the hover surface. You can see this. So this is the surface for the hover surface, and this is the tension cutoff. Fine. Now, now we have this Roscoe surface, hover slave surface, and we have the tension cutoff. We can present a complete, we can say state boundary surface. That's called a complete state boundary surface. That actually is a boundary that defines all possible states of a remodeled soil, and soil cannot exist beyond this CSVS. So you can see this is the QV. Fine. So in 3D QVP dash, we can see there is the this is the one bound, this is another bound, and this is another bound. So log spiral curve, if we like, since if in the CCM and MCCM, if we since they are actually following the associated rule, so if we replace the functions with the logarithm spiral or ellipse, then we can get a response like this, or the boundary surface will be like this. Fine. So this is the tension cutoff zone, and this is the what's called as hover slave surface, and this is the Roscoe surface. Fine. Here, this represents, you can see in the log spiral for the if we talk about CCM and MCC, and this is the general representation for tension cutoff. This is the Haversley surface and this is the Roscoe surface. They are actually the bounds, nothing more than that. Now, moving on to the example problems. So we'll start directly. So soil surface or sample was isotropically consolidated to 300 kPa, and initial specific volume is 2. Soil was subject to a drained compression. Determine the final stress, final specific volume, and volumetric state and area. Critical state parameters are given. So we have been asked to determine these parameters. The critical state parameters are given. The naught is 3, lambda is 0.3, kappa is 3.2, and m is 0.5. So we'll start. Now, we know that for the failure, we have been given the isotropic pressure at 300 kPa, correct? Fine. Now, we know the relation between the failure stress and the this consolidated, like the P naught, that is a relationship with the like the P F dash, which is the final stress, and P dash naught, which is the isotropically consolidated stress. We have a relation between them. So we'll try to get that first. So we'll use that first. So we'll write Pf dash is equivalent to 3 times P naught dash divided by 3 minus M. So this will relate the failure stress with the consolidation stress. So 3 into P naught dash is 300 divided by 3 minus M is 0.5. So once you will calculate it, you will get 360 kP. Fine. Now you know this M, so we can relate the QF is equal to M times PF dash. Fine, because this point will lie on the critical state line, so we can relate these two. So this is 0.5 into 360, it is 180 kP. These are the failure stresses. Now we need to find the final specific volume and the volumetric strain. Now we know the equation V final is equal to gamma minus kappa minus lambda ln of P. Fine. At the failure point, we can relate this uh, from the critical state line. So Vf is equal to gamma is 3.2 minus lambda is 0.3 ln of Ef dash is 360. So you will get Vf is equal to 1.434. Now volumetric strain, final volumetric strain is given by delta V divided by V naught into 100. Fine. So change in the specific volume. So initial, so final specific volume is 1.434 and initial specific volume is 2 minus 2. We have minus second side divided by initial specific volume, that is 200. So you will get 28.3%. So this is the specific, this is the volumetric strain at the failure. Now we have another question. Soil sample was isotropically consolidated under a cell pressure of 200 kPa and unloaded to a mean stress of 100 kPa. Drain sharing is performed to determine the principal stress at yield. So what I have been told, for example, this is our P dash Q. This is the yield surface corresponding to the isotropic consolidation state of 200, and then we have loaded the sample to 100. Somewhere here it is 100. Fine. If this is the critical state line, fine. Drain shear is performed through this, and we have the drain sharing. So we need to find the principal stress at yield. So this point we need to find the critical state. Sorry, the principal stress points correspond to this. So once we have we know the yield points, right? Once we know the P and Q corresponding to this, like the yield point, we represent it by P dash O Y. So once we know this P dash O Y, we will be able to calculate the principal stresses. And this is Q dash, not represented by Q. We are not. Fine. We have to determine. We will determine first this P and Q, and P and Q will be able to determine the I mean we'll be able to determine the mean stresses, principal stresses. So first of all, we will try to determine this P dash OY and Q naught or P naught dash Y, Q naught dash Y corresponding to this uh, point per B. And since it lies in the yield surface, so we can use the yield surface and try to get the P and Q corresponding to point B. Fine. So what is the equation for the yield curve? We write it is in general I am writing P dash square minus P dash Py dash plus Q square divided by M square is equal to 0. This Q, this P dash corresponds to this. P dash Y is here. P dash is again P dash Y. Q square is Qy. Fine. So we can write P dash not square minus what is it? P is 200 into P dash not Y plus Qy square divided by M square. Now M we can find from this. So we can write M is equivalent to 6 sine of 25 degrees divided by 3 minus sine of 25 degrees. So M is equivalent to 0.983. 0.983 square is equal to 0. Fine. M square. Now I will try to solve it with you only. Fine. Yeah. M square is 0.983 square. Fine. Now another thing we can do is since we know this point q naught y, it can be determined from we know the slope for this line, so we can relate this q and this p naught. Fine. Using this triangle part. Fine. So we can write qy is equivalent to 3 times p naught y dash minus 100. Okay, that I represent. We can represent by qy simply. Fine. So qy is 3 times p dash y, p naught dash y minus 100. So you replace this. So p dash naught y square minus 200 into p naught y dash y plus 3 into 3 is 9 p dash 100 whole square divided by 0.983 whole square is equal to 0. Fine. So we will try to solve it. So we will try first we will check this term, that is 9 divided by 0.98, 0.983 square is equal to 0.966. 0.966. It is p dash 0 y square plus tan is by 4 minus 200 times p dash y. Fine. So 9 divided by 0.966. This will be equivalent to it's 9.316 p dash 0 y square plus 93167 minus 200 into 9 divided by 0.966 1863.3 b dash. Fine. So now we will replace this. This is 10 point around 10.316 b dash here. So once we will replace this here, we will like this and this term will add. So this and this term will again they will add up. So 1863.3 plus 200. So both the terms are negative. It will be minus 2063.35 P naught hy plus this is the constant term 93167 is equal to 0. Now we try to solve it. 10.316 and we have minus 2063.65 and 93167. We'll get two roots for it. 131 kPa. I will write it 1 and P dash 1 2, which is equal to 68.86 kPa. Now we got two roots. We have to select which one to use. So if you see that if you use this Qy, fine. Now if P naught y dash is less than 100, so Q will be negative. So this we can't use because our Q cannot be negative. It should be a positive term. So therefore P naught dash y is equal to 131 kPa. Fine. And correspond to this Qy is equal to Q will be equal to 3 into 131 minus 100. So which is equal to 93 kPa. Which is 93 kPa. Correct? So now we got this point. This point we got. What are the coordinates of this yield point? Now corresponding to this, we need to find the principal stresses. Now we know that P naught, yeah, P naught dash y is equal to sigma 1 dash plus 2 times sigma 3 dash by 3 basic formulations, and Qy can be written as sigma 1 dash minus sigma 3 dash. So sigma 1 dash can be written as Qy is 93 plus sigma 3 dash. We replace here. So P naught dash y is equal to 131 into 3 is equal to this is 93 plus 3 times sigma 3 dash. Fine. So 131 into 3 minus 93 divided by 3, we will get sigma 3 dash is 100 and sigma 1 dash is equal to 190 kPa. So these are the principal stresses corresponding to the yield stress. So what we have done, we have just solved the yield curve, modified Campley yield curve for the points, for point this to and by using the details of like M and the stresses. We got the P and Y. Fine. From P and Y, use the basic equations of sigma, like the basic, I can say basic equations which relate the P, which is the mean stress with the vertical and or horizontal related stresses. Fine. So from that, we will get the sigma 1 and sigma. Moving to question number 3. Soil was isotropically consolidated at 200 kPa, fine, and unloaded to 100 kPa. Initial specific volume is 2 Vk, which is the specific volume corresponding to the 1 kPa. The mean stress at yield is 150 kPa. The bulk modulus we need to determine. So this information we have been given. Fine, we need to determine the bulk modulus. So we know that we know if we know the formations for bulk modulus, K dash is equal to 1 plus P naught divided by kappa into P dash. Correct? Recently we have like just now we studied that this P dash can be considered as the average of the yield stress unloading point 150 plus 100 divided by 125 kPa. Fine. Now V is equal to Vk minus kappa times ln of P dash. V is 2, V kappa is 2.4 minus Kappa we need to find ln of 125. Fine. So corresponding to this point, this P dash, V is given as 2 and the initial like for 1 kPa V kappa is 2.4. From here we will get the value of kappa. So we will get the value of kappa is equal to 2.4 minus 2 divided by ln of 125. Oh, sorry. Here will be ln of P dash and this P dash corresponding to the unloading point. It's 100. Fine. It is 2.4 minus 2 divided by ln of 100 and it will be equal to 0.086. Correct? Now, what is missing now? E naught. So we know that specific volume is equal to 1 plus E naught. So specific volume is going to be 2. V naught is 2. 1 plus E naught. So implies E naught is equal to 1. So we can now determine K dash is equal to 1 plus 1 divided by kappa is 0.086 divided by P dash. Fine. It's P naught dash, sorry. Correspond to initial state. So V naught is called Vk minus K ln of P naught dash. So this P naught dash is correspond to the unloading point, that is unloaded, like the final unloaded point as 100 kPa. Fine. So we get kappa, from kappa we'll get the K dash is 1 plus 1 divided by 0.03 into P dash is 125. So what is the value? It's 2 divided by 0.086 into 125. That is 2906 kPa. Fine. You can write into kPa, that's not an issue. In MPa, it will be divided by like when it like divided by 2906 kPa. So divided by 1000, so that will be 2.9 MP. Right. Now, final question: a soil sample is isotropically consolidated to at 500 kPa and then unloaded to 300 kPa. Fine. Initial void ratio at 300 kPa is 0.9. Drain shear is conducted. Volumetric elastic strain up to initial yield is. So we need to find the volumetric strain out to the yield. Fine. So what are the things we have been given? We have given the initial, like the consolidation point, unloading point, initial void ratio at 300 kPa. We need to, and the critical state parameters are also given. Now again, similar to the one we have done here, we'll use the again. We need to find the yield stress, and once we get the yield stress, and we will use the equation for the like we have the if we write the equation for the strain, elastic strain, is it is equal to kappa divided by 1 plus P naught ln of Py dash divided by P naught dash. So kappa is 0.04 divided by 1 plus P naught is 0.9 into ln of Py dash is missing and this P naught dash is 300. So we need to find the P dash y, which is the yield point. So again, we will take use of the yield curve plus P naught y dash square plus P naught dash y P naught P naught dash plus Q square by M square is equal to 0. Fine. So same exercise. So P dash naught square plus 500 times P naught y dash plus Q we will write in terms of Q is equal to 3 times P naught dash y minus P naught. Fine. This P naught is 300. So 3 is P naught dash y minus P naught is 300. So we write here 9 times P naught dash y minus 300 the whole square. Here m is 1.1 square is equal to 0. So actually P naught dash y square plus 500 P naught dash y plus Once you will solve it, you will get the final equation as 10.21 P naught dash y minus 6005 P naught dash y plus 8100. 4 times 0 is equal to 0. You will get two values of P. One is 386 kPa and P naught 2 is equal to 200 kPa, 201 kPa. Now again, this P naught dash y less than 300 is not acceptable. So it means that our P naught dash y 1 or P naught dash y simply equal to 386 kPa. Fine. So can we find the delta epsilon P dash E is equal to this term is equivalent to 0.02105 into ln of 386 divided by 300. That is 0.02105 into ln of what is the value 386 by 300, 0.252 into 0.02105, that is 0.005. So the elastic component of the strain or the volumetric strain is after the yield point is 0.005. Fine. So that was the last problem that I want to solve with you. So just a recap what we started with. We started with the prediction of solar failure for the NC and LOC using the four plots QP dash Q stress strain, specific volume versus ln of P dash and volumetric strain versus axial strain. Then what what is the need of this intermediate intermediate yield curve? It's for understanding the things, how the failure how the failure state is reached. Fine. Then similarly for CU test, how the prediction of the failure can be observed or can be determined using the modified Cantley model or the critical state framework. Then the prediction of the failure for HOC in terms of drained and undrained conditions. Then the effect of ESP, how the slope on the ESP affects the response, or even if we have the ESP2, it can even if it looks like NC or LOC, its response is more like a HOC because it is going to yield first, after that it will reach the failure. So ESP, slope of ESP will influence the manner in which the failure occurs. Then determination of soil stiffness, these three equations. Then the variation of soil stiffness, three zones were determined: small strain, intermediate strain, large strain. Elastic response, there's a lot of degradation in the intermediate strain, and large strain it reaches the critical state while there will be a plastic flow. The determination of strain from the modified Cantley model, we told that the total volumetric strain can be determined, like it can be separated into the elastic component and plastic component. So we first determined the total volumetric strain from EA to EB, fine, which corresponds to the expansion of the yield curve from D to C, fine. We formatted the equation for the total volumetric strain. Then we formatted the equation for the elastic strain, and plastic strain we determined from the subtraction of these two. Then we determined the shear strain. We have told that the yield surfaces in this modified Cantley model and Cantley model, they are associated flow rule in which the yield function is used. A similar yield function describes the is used to describe the plastic potential function also. So it follows, and it also follows the normality rule. So the plastic strain component increment delta epsilon P for a given stress increment is normal to the plastic potential function. So we first determine the plastic potential function, and we first determine the plastic normal function using the slope equations of slope and normals of the yield function to determine this plastic strain. Fine. So this component was known to us. We just determined this. Fine. After that, we told that we're interested in the state bound surface. Like, is there any state? Since we are telling that on the from the week 4 or 5 that on the right side of NCL there is no state possible. Similarly, if we go in the like in this direction, the vertical direction, for the HOC have a bound that they can't pass this peak state, and we can't unload the soil beyond its tensional cutoff. So for this portion on the wet side of CSL, that is this portion right side, is there a bound? So that bound we determine experimentally. Like we have seen that that bound we can determine using that bound is called the Roscoe surface, and this peak state we call the uh, Hurlius surface. I don't know whether this pronunciation is correct. We will see it. And then the 3D representation of critical state in the 3Q specific volume and P dash plots. We have the drain plane, and after that we have the undrained plane. We determine the failure, how the critical state is how the soil the set of soil is the critical state in both drained and undrained parts. Then we determine whether different drained and drained ESPs will have a similar specific volume where it crosses each other to determine the bound on the wet side of this on the wet side of the CSL. Fine. So that surface is called the Roscoe surface. Fine. And for the peak state of HOC, which is on the dry state, like on the wet side of the CSL, we have the Roscoe surface, and for the dry side of the this critical state, we have the hover sleeve surface. Fine. This is for this. Fine. So we get a complete boundary surface. We have the tension cutoff. We have the what's called hover sleeve surface here, and we have the Roscoe surface here. Fine. This is the complete bound that we have for the all possible states of the removed soils. Fine. So if we talk about the CCM and MCCM, so this is the curves that we get for the that we obtain for the boundary surfaces. Fine. So then we solve few numericals. Fine. So this is all I have for today's presentation or for today's session. So if you have any doubt, you can reach out in the form, and this is probably the last session I will be taking. So in case you have any doubt, you can reach out to me in the form or you can email. So best of luck for your assignments and best of luck for your this exams that will be there. So please write to us if you have any doubt. So I will be answering you in the form. So I will stop the recording here. So meeting will be there up to 9 o'clock. So if you have any doubt, you can just ask me. Thank you.